Here we can see an oblique triangle. We don't have any right angles, which would make this pretty easy to solve. I know one side length, which is side AC, which has a length of 27. And I know two angles. I know angle C and I know angle B, with 103 degrees and 28 degrees respectively. What I might start off by doing is writing my law of sines up top, just to help me remember it. Sine C over C equals sine B over B equals sine A over A. Now what I'd like you to remember is that the uppercase letters are referencing angles and the lowercase letters are referencing the lengths of a side. This problem goes on a little bit further to ask us to find angle A and side lengths C and A. Let's start with angle A, because we know a trick to do that from geometry. We remember, hopefully, that the sum of the angles of a triangle will always equal 180 degrees. So if I begin to set this up, I know 180 minus the other two angles will give me my remaining angle. So 180 minus 103 is going to be 77. Minus 28 more should give us 49. Alright. For the other ones, I'm going to have to use this law of sines then, because I don't have a good way to figure out side C or side A without doing some trig manipulation unless I use this. So let's take a look. Let's start by maybe finding side C. Okay. Side C, I don't know, but I do know the measure of angle C, which is 103 degrees. Alright, I do know both parts of angle B and the side that measures B. And that's going to give us sine of 28 degrees divided by 27. Once again, make sure your calculator is in degrees instead of radians, and begin plugging these things in. If I do sine of 28 degrees, close my parentheses, divide by 27, I get 0.01, and let's go 0.17, carry it out to 3 places. I can type in sine 103, and I arrive at 0.974, divide by C. With a little bit of algebraic manipulation, I multiply both sides by C. Cancels to 1 on the left. And then I'm going to divide both sides by 0.017. I'm going to arrive at an answer, which tells me that C is equal to 57.316. And let's see if that makes some sense. Angle C is 103 degrees. It's the biggest angle out of these three. Angle B is significantly smaller than angle C. And it looks to me like side B, which is 27, is also significantly smaller than side C, 57. So that makes some sense. Okay, let's find side A. Well, I know sine of angle A, which is 49 degrees, divide by the measure of A, equals, and you know, I can just use the same value over here since I already calculated it. So that's going to be sine of 28 divided by 27. And we figured out that was 0.017. Okay? Using the calculator, sine of 49 degrees is 0.755 with some quick algebra. I can arrive at an answer of 44.39 for A. And once again, that kind of makes sense. A measure of 49 degrees is between 28 and 103. The side measure of 44 is between 27 and 57. Looking at a second example, this time only trying to solve for 1, we can see a more typical type of application. This was originally taken from a telephone pole problem that I decided to break down just to look at the triangle and the process of doing this. Okay? Somewhere useful to start is always going to be looking at the angles of the triangle and trying to flesh out all three. In this case, I know two angles, and I know the side that's between them. If you remember from geometry class, this was an ASA relationship, a side between two angles. And in fact, if I look for the third angle, I can do the same thing, where angle C has a measure equal to 180 minus 98 minus 43. 180 minus 98 should be 72. Minus 43 should take us down to 29 degrees. Awesome. We can begin to solve for this thing. I know that I'm going to be using my law of sines. That's going to be sine A over A equals sine B over B equals sine C over C. In this case, the only values that I know both the length and the angle for, now that I've figured out the C, are going to be C. So angle C becomes 29 degrees, and side C becomes 22. Since it's A that I'm looking for, I'm going to put my angle A in, 43 degrees, and the side length A is what I'm going to solve for. To clean this up a little bit, I now have sine of 43 divided by A equals sine of 29 degrees divided by 22. Once again, we use our calculators to calculate these values. Sine 29, close parentheses, divided by 22 is going to be 0.022. Sine of 43 is going to give us 0.682 divided by A. With some algebra, I arrive at A is equal to 30.999, which is rounded up to 31. If we look at our angles and our sides, angle C was 29 with a side length of 22. Angle A is larger at 43 and appears to have a side length of 31. Since 31 is bigger than 22, that makes sense. sometimes the law of sines is not going to work quite the way you want it to. I'd like you to remember back in geometry when you were studying triangle congruence and one of the cases didn't work. You had AAS, ASA, SAS, SSS, and then you had the right triangle theorems. The problem was when you had two sides and the non-included angle. So if I were to draw a triangle where this would be an example, if I knew something about two sides and the angle that's not between them. So let's go with that one up there. This would be an SSA relationship. And just like in geometry, this produced more than one triangle rather than a congruence setup. The law of sines, when you have this relationship in the triangle, will occasionally have no solution or two solution cases. We're going to look a little bit more closely at this when we play with some of these problems in class, but I wanted to make you aware of that for when you try some of these problems. If you get an answer that has no solution or might have two solutions, you should be ready for that. Okay, that's all we've got for this lecture. There are some example problems with some support videos that I've taken from other sources available on the website, and we'll see what we can do playing with these problems tomorrow.